Hello and welcome everybody to Coffee with Cluster One. My name's Sven, and I'll be your host for today. Yeah, I'm very happy to introduce you to our speaker today, which is Emmanuel Ameisen, who's the AI lead at Inside Data Science. And yeah, he'll talk about how to bring the domains of natural language processing and computer vision together and solve real-world problems that he has encountered in industry projects he's led over the years. So it's going to be super exciting. It's going to be a very hands-on talk. And yeah, the entire webinar will last about 1 hour. And we're definitely welcoming your questions throughout. So Emmanuel's told me that he likes to answer questions in the flow of the presentation. So feel free to post any questions you have in the chat. And yeah, and if there are any questions left open after the presentation, we'll address them then. But yeah, so we want this to be as interactive as possible, so ask away. We're excited for your questions. After the webinar, we'll send you an email, or we send you a link to the slides, and we'll also make the recording of this available on YouTube later. Yeah, before I give the stage to Emmanuel, let me give you a little overview to what we do at Cluster One. So I wish I could, oh, there we go. So at Cluster One, we're on a mission to scale AI. We're a deep learning platform, and that allows you to run machine learning and deep learning code on a distributed system, but without the hassle of doing like cluster management and infrastructure setup. So Cluster One runs on systems of any scale, and we support any infrastructure. So no matter if you're running on AWS, on GCP, Azure, an on-premise installation, or any hybrid of the above. Yeah. So we were founded in October 2016 by graduates from Stanford and UC Irvine, and by researchers from Google X. We launched our product last year in August, and in December we received funding from Paul Allen's Institute for Artificial Intelligence. Yeah, if you want to come up and say hi, we're headquartered in Seattle. We also have offices in Palo Alto, in Poland, and Canada. So yeah, how can Cluster One help your business? Well, we accelerate your deep learning research by providing easy access to a scalable deep learning infrastructure and distributed training. So you don't have to worry about setup and anything, but can focus on training models. Yeah, we take the DevOps out of your projects. So instead of spending time doing setup and focusing on infrastructure, you can focus on what matters to your work. So you can focus on creating benefit for your company. Yeah, but while we're doing this, we also don't restrict your choice of infrastructure. So whatever setup you have, Cluster One can run on it. And you can even modify it and like switch it up between cloud and on-premise. Whatever works best for you, we'll handle it. Yeah, here's a, excuse me, here's a little high-level overview of our platform. So as I said before, we support any kind of infrastructure, if it's in compute and storage and code. And we're sort of the operating system for your deep learning projects above that. So we provide orchestration, we provide access control, job monitoring, management, and all that. And on top of that, so on the data scientist end of things, we support a variety of different machine learning frameworks, be it TensorFlow, PyTorch, using Keras or Jupyter notebooks, but all patches are then seamlessly without any setup work on your side into Cluster One. Yeah, if you want to know more about us, feel free to pop by our website, cluster1.com, and leave us a message via intercom or send us an email. We're happy to hear from you. Yeah, but now it's time for me to pass over the mic to Emmanuel, and yeah, let's hear his presentation. Emmanuel, stage is yours.
Awesome. Yeah, thanks, Sim, and thanks, Cluster One, for having me. I'll just share my screen here. We can get started. There we go. All right. Hopefully you can all see my screen. And yeah, so again, thanks for the invitation. So today I sort of wanted to talk about NLP and computer vision, as Sven mentioned, and I think a lot of us might be familiar a little bit with one of these words, with NLP, with computer vision, or just have general curiosity. how they both sort of mix and match is something that I found more and more interesting over our experience at Insight, sort of building these projects. And so I wanted to give both an overview of what we've seen work and what we've seen be harder and tricky, but also dive deeper into just like an example with actual code and show you the sort of things you can do and that you might not be aware of. So I'll start by sort of chatting a little bit about just why I'm giving this talk and like how I've gotten this experience. So I'll keep this very brief, but basically, and I know there's a couple of people that are Insight Fellows in the audience, so they know this, but Insight's a 7-week fellowship. And so it's a free program that's all over the US, and I'm the lead of the AI program in Silicon Valley. And so what that means is I have been with the program since it started, and I've helped lead projects. And so what I mean by projects is that Insight works with a bunch of companies, all of these here, and has a huge network of fellows that have come through the program. And the way that the program works is that these fellows will come to Insight, then they'll build a self-standing deep learning project for 4 weeks in the case of the AI program, and then interview with these companies. And so example of projects include, building a fashion classifier for a fashion startup, building something that automatically generates Yelp reviews, reading text and videos, delivering solutions for ultrasound segmentation or MRI segmentation for heart disease diagnosis, doing support request classification, et cetera, et cetera. There's a lot of projects. There's as many projects as there has been fellows that have gone through the program. In the AI program, we've had a lot of projects be, in partnership with companies where we help them build some part of their pipeline. A lot of these projects are either NLP or computer vision, and some of these projects are both. And that's going to be sort of the focus of those, is what we've learned through, the sort of hundreds of projects that we've built at Insight. Cool. So what are we going to sort of talk about overall? This is a very high-level overview. We're definitely not going to spend the same amount of time on each of those bullet points. But the first two, I just wanted to sort of give a quick overview of both computer vision and natural language processing. And so this is definitely a thing where I'll go a little quick. So please feel free to stop me if something's not clear. And then I'll talk about, okay, so how we combine both? What are the interesting challenges, the things that we've learned? And then I'll talk about sort of, you'll see, based on these challenges, what are sort of the fixes that we've seen in the industry for NLP and for computer vision? And then combining both, I'll give you a demo of how you can actually do that on your laptop. So let's start with computer vision. So I think most people that are interested in deep learning are pretty familiar with sort of how it's applied to computer vision. That's how the whole deep learning boom started. Image classification on MNIST and CFAR, and most importantly, ImageNet in 2012 was when sort of deep learning models started overtaking classical computer vision models, and when people started really being interested in deep learning. So that's sort of how the field started. There's then other tasks on top of it, which are object detection, where you just try to not only say what's in an image, but where it is. Image segmentation, where you just do even more fine grade and you say which pixels are which. And then generative models, where you're trying to do super resolution of an image, or colorize black and white images, or do style transfer, where you take a picture and make it look like a Van Gogh. And so a lot of these models, I think, are pretty well studied now. What we have found is that as soon as you go away from traditional computer vision tasks, which are, I would say, are mainly classification, detection, and segmentation. So for example, the fourth one here, pose estimation, it becomes very hard and the models become very complex very fast. So that's definitely something that is already happening in the most well-studied field of deep learning. So then there's NLP. So NLP, we have sort of the similar stuff. We have classification, where you do sentiment analysis, or you do spam detection. Code classification is another one that we did for a company that tries to grade software engineers based on snippets of code. And so can you automate that using NLP? But those are all very common tasks that Insight Fellows will do with companies. And then there's sort of other stuff like named entity recognition. That's very useful for chatbots, where somebody's talking to your chatbot, and you want to extract, what if they say like, oh, my name is Emmanuel. You want to extract that in that sentence, Emmanuel is a first name, and remember that for the next time you address them. Information extraction, translation, text generation. I would say a general trend that we've seen in NLP is that it seems to always be, in terms of the complexity of models and how elaborate they are, in terms of the deep learning aspect only. They're always sort of maybe a couple of years behind images, because I think everything started with images, and then these, innovations like residual networks that were first invented for images then get translated back to NLP a little later. So it's interesting to see the field grow, but grow just a little behind images very often. So then, the sort of topic of the talk is to combine NLP and CV applications. And so in deep learning, especially, what's really fascinating is that you can think of an endless amount of applications for everything. So I narrowed it down to a few here, and sort of three categories. So if you combine both, you can imagine that you can go from one to the other, or you can sort of find something joint for them. And so going from image to text, the real common applications are image captioning and video captioning. That's when you describe an image or a video. So, if I give you an image and you tell me like, oh, this is what's in the image, extracting text from videos, this is super useful for advertisers, for example. We've worked with companies that want to be able to take a bunch of videos and say like, okay, what are the lines of text that are present? And could you just spit them out as raw text from the image files? Generating code from drawings, we'll go into that in a minute. It's actually also an image to text problem. And then text to image, where you generate video thumbnails from a description, or generate images. We'll talk a little bit less about this one, because I mentioned it mostly for completeness, but I think it's much more rare to see it used in industry. So I wanted to focus this sort of on actual practical applications. And finally, semantic search. This is used a lot and is sort of a catch-all term, but what I meant to say is, how can you search through your images by using text? So, Google image search, or even if you're on your local phone, you have a lot of applications where you can find, all photos of trees, or all photos of people, or all photos of cars. And the opposite, how can you get text from images? So sometimes you want to extract tags from images, or do image captioning as above. Cool. So I'll start with image captioning. So this is a pretty standard image captioning model. This is the point where I imagine that maybe a few of you are a little curious about things, so I'll try to explain it. But if there's any questions, feel free to ask. So the idea is that you pass in this image at the bottom of a horse here, and you want to get the description of the image. So on the top right, you see it says, well, I have the video here. Okay. It says a horse is standing in a field with a fence in the background. And so this is a pretty standard architecture that I'm depicting here for image captioning, where you take the image, you pass it in a convolutional neural network, which are very good at extracting features from images, and then you feed that into an LSTM or another recurrent model that will sort of learn to spit out descriptions of images based on the first image that you sort of fed it. And so what I think is interesting here is that you use a language modeling approach. If you remove that left part where you just put the CNN into the LSTM, you've trained a language model, right? Which is learning a distribution over words. So this is very similar to the way that you generate Yelp reviews or generate text from, fake Shakespeare works, is you just go over text and learn how it's structured. Very similarly, you just add a CNN at the start, and you manage to get to a model that can actually reproduce good captions. This is from the test set, by the way, so it's a pretty good caption. And yeah, you just prime it with features extracted from a CNN. Seems almost too good to be true. I think, whoops. No, that's not great. Okay. Let me just stop sharing for a second and find my PowerPoint, and I'll be right back with you. That's a new one. Okay. There we go. All right. Cool. Hopefully this time it stays alive. All right. You see my screen?
Yeah.
Cool. Awesome. So let's try this again. So yeah, as I was saying, so what's interesting is this is end-to-end, this whole image captioning model, which makes it particularly efficient to train. You just put images at the start, put text at the end, and let the network do its magic, but very hard to debug. When it works, it works. When it doesn't work, it's super hard to see whether your convolutional neural network is a source of the problem, or whether it's your recurrent neural network, and you need to really dive deep and have a good understanding of these models. So then I want to talk about code generation. And this is fascinating to me because this is a project that we did recently where you sketch out a website, and from the sketch of the website, you learn to generate HTML for the website. Now, what's really cool about this to me is that this is much harder for humans than image captioning, right? Like pretty much anybody that is over the age of 10, you can show them an image and you just say like, hey, describe what's in the image, and they'll do a pretty good job at it. Very few people can actually take a sketch from somebody and generate HTML. That's an entire profession. But it turns out that in terms of how you do that with machine learning, you use exactly the same model. So here you can see, you chuck the image into a convolutional neural network. You chuck the HTML, so your labels for your training set, into a GRU, which is just another recurrent neural network. And then you output sort of the predictions, and you get a model. So I think what's really interesting here is that the trick's only in getting the data, and you don't have to do any changes to the architecture, but also it shows how our intuition for what might work when you combine these models is often very wrong, right? So, most people would think that image captioning is very easy and this is very hard, but it turns out that once you get the proper data set, they're basically the same sort of difficulty. Next, I want to talk about text extraction. So this is the opposite of the previous example. If I tell you, look at this image and tell me what lines of text are on it, it seems strictly easier than describing what's in the image, right? Describing what's in the image requires some level of abstract thought where you're like, okay, well, I'm going to describe at a high level what's going on here. But just reading the text is super simple. You just literally, if you know how to read, then you solve that task. In deep learning, the way that you do this is super complicated, I find. Is the only way that we found to make it work, and we found in the literature, is that you need to have one first network that just sort of looks over the whole image, is like, oh, well, what's text, what's not text? And then you need a second network that takes in the output of this first network and transcribes the text. And what ends up happening is that, well, when your first network gets it wrong, then your second network gets it wrong. And you have to efficiently manage to basically make both networks communicate so that the second network can propagate its loss back and say like, oh, hold on, like the reason I couldn't read this because you detected this offset by a few pixels up, etc. And so just that takes a lot of engineering and is very hard, and yet it's something that's super simple for humans. A side note is that the architecture that you end up building is closer to an architecture that you would use for speech recognition rather than the one that we use for image captioning. And so I think that this is, like, just to add sort of insult to injury here, not only is this task that looks simpler much harder, it's also the way that we think about it as humans is, oh, this is very close to describing an image, but the way that you should think about it if you're doing deep learning is like, oh, this is very close to doing speech recognition, which is a completely different problem for us humans. So I think that's sort of been an interesting learning experience. And finally, I wanted to sort of talk about visual Q&A. Because this one, I think what's interesting about it is that it's the same for humans and much harder for machines. So meaning, if somebody can transcribe an image, if like you can give them an image and they can describe what's in the image to you, then presumably if you ask them questions about the image, they can answer them. So here in this example on the left, you have a picture of, it's a little small, a picture of two horses and two people sort of petting them. And the question is, how many horses are in the image? And the answer is 2. So you can train models to do this. It turns out that you have to do a very hacky thing where instead of letting the model answer freely, you just rank the 1,000 most frequent answers, like 2, 7, blue, red, and then you sort of rank the outputs based on some embedding. And so you're doing this very hacky thing that honestly works very poorly outside of your training split. And yet for humans, it seems like just the same problem. So I think the main takeaway from just doing all these projects is that humans especially are very bad at estimating what will be easy and what will be hard in terms of training these mixed models. And so having a good understanding of the literature of what's done before and being able to go across domains to find similar architectures has been super useful. There's another issue though, and this is sort of going to be the point of the rest of the talk, which is, what does it scale here? Which is that these methods sort of mix and match many different architectures. And the combined representation of computer vision plus NLP is often learned implicitly, right? You put one thing at the start, one thing at the end, and then you just let the network figure it out. And so you don't really have much control over how it learns these representations and what it does. What's interesting about this is twofold. One, it means that it's super hard to cache and optimize. A lot of deep learning projects, I think, are, hey, like I built this on my local AWS instance and I can serve it and it works great. But what if you wanted to do image captioning as a service? Then you need to make sure that you can handle thousands and thousands of requests at a given time. And so any speed up that you can have is super important. It's also hard to reuse across services. I think one of the great benefits of deep learning is you can learn great representations, but here you can't really extract them from this mush of a just big ball of models. And so basically they're entangled. And so the question is, what if we want to learn a simple joint representation of text and images that is useful? To answer that.
Hey, Emmanuel, let me interrupt you here really quick because we have a question from the audience. And the question is, if you could elaborate a little more about combining training for CNNs and GRUs, if there's like specific challenges that are there, or.
Yeah, sure. I mean, at a high level, there's not any specific issues with like CNNs and GRUs as opposed to CNNs and LSTMs or other combination. It's mostly the issues that we've seen mostly come from once you combine both. So here in this example, for example, we have the CNN, the feature it extracts, so the sort of the last layer, and we'll go more in depth in this, are concatenated with the GRU cell at each step, and you predict things. And experimentally, that works better than this approach does before, where you take the features and you put them only in the first step. Why it works better by repeating them at each step, I have no idea. And this is a lot of what we found in practice at Insight, is that there's a lot of times you have to post-rationalize your theory, because intuitively it seems like you wouldn't need to repeat features at every step here if you didn't need to do it here, but yet you do. And why that's the case, unsure. But as far as using GRUs versus LSTMs, I don't think there's anything specific that comes to mind. I mean, they have different properties, but nothing worth mentioning here, I think.
Cool, thank you. Yeah, one more question.
Yeah.
You mentioned that some networks are hard to reuse across services. Somebody asks what you mean by that, if you could elaborate on that.
Yeah, so that's a very good question. So basically the idea is, so what if let's take an example. What if here, like you train this network and it's great at doing question answering, and you're this online image platform and you do question and answering as a service. People can maybe for accessibility, there's an image and they can ask you questions about it, and you put responses. Presumably, if you've built all of this already, you could also offer a service. Let's say that you want to do the first thing that we're talking about, image captioning. So not only do I want to be able to ask questions and get answers, but I also want you to like just provide a description for me. Well, in this current paradigm, if you train them with these sort of state-of-the-arts model, you're going to have to train two entirely separate models, which is kind of crazy if you think about it, because you would imagine that that first part that takes in the image and generates features would sort of generalize well, and that you could just like take that part away from the model and plug it in the other model. It turns out that in practice, this very rarely works, and often you have to retrain everything end to end. And so it seems like a huge waste of resources that you can't reuse this efficiently. All right, and we'll go more in depth into like what reusing these mean with this case study. What's interesting here is I think I'm going to go through this pretty quickly, but the main point is I think most of you are probably familiar with Google Smart Reply. And I want to talk sort of about the issues they had and how they faced them. This is purely an NLP sort of domain tasks, but it turns out that what they did, you can use to then combine NLP and computer vision. So, okay, so Google Smart Reply is simply you get an email, and then Google here, you can see at the bottom, sort of suggests to you ways to reply to this email. The naive way of doing this is you get the email, you process it, you put it in a recurrent model, and then the recurrent model learns the outputs. This turns out to just not work. You get very severe sort of mode collapse where your network just always answers the same thing, which is like the most common answer. You can't really control the quality of responses, and it's, again, super expensive to run an LSTM every time you get an email. So Google, I'm not going to go in depth on this, but basically Google just tried like a bunch of methods to make this faster and more efficient. And they describe all this in the paper that you can see at the bottom right. And they have like this new approach where they have a network that decides whether they want to run the network, and then they do clustering and re-ranking. But it turns out that around 10% of all emails sent through Gmail are smart reply, and that's a lot of LSTM inference calls. You can imagine the volume of emails being sent. If every time an email is sent, you need to spend 10 seconds to run inference on LSTM, that's crazy. And so they restricted the outputs, the replies they could suggest, to a smaller subset. And once they did that, basically they transformed the sequence-to-sequence problem in a search problem. And the way that they solve the search problem is by learning intelligent embeddings. And so these reusable representations that we were talking about, these are what these embeddings are. And so you might be familiar with word embeddings. For the ones that aren't, I'll just go very quickly over it. The idea is you have a method by which you can take a word and transform it into a vector. So think of like, usually they're size 300, but here, like we've described them as size 3 for simplicity. And these vectors will capture the semantic meaning of words. So you'll have, man to woman, their relationship, their difference in vector space will be the same as king to queen. It'll be gender. You'll have all of the capitals of countries that will be in a similar space to each other, and all of the countries be similar to each other. So basically, you'll just have vectors that close words will be close to each other, and words that are very different will be far from each other. So that's the idea of the word embeddings. It's from 2013 and has sort of taken the field of NLP by storm. And here, you can see it's basically an embedding. So these are word embeddings. But embedding is associating any entity. So it can be a word, or it can be a body of text, or it can be an image to a vector here. So you have these vectors of words that have some sort of meaning. And so the idea of Google is like, okay, well, why don't we just do email embeddings? And they did that and basically have a model where instead of learning this complex LSTM, they just learn a way to put similar emails in a similar location in this vector space and put the responses in a close by location. So this is their updated model. They don't have an LSTM anymore. They just learned these embeddings. And maybe this doesn't seem like a huge deal, but basically before they had to do inference at every time they got input and try to predict use a very costly model to predict. And now, because they have all these embeddings and they already know all the responses, they can cache all of that bottom part. And at inference time, they only need to do a dot product. So to put it maybe more concretely, because we're sort of like diving deep in the weeds, if you look at what it did for Smart Reply, the conversion, meaning how many people used the replies, basically didn't change. It got better by 4%. And the latency got reduced by 2 orders of magnitude, which is gigantic. And so the lessons learned is that you don't always need a complex model, and you can use smart engineering work to reduce complexity. So now, and deep learning is extremely good at learning representations. So now I want to sort of say like, okay, well, can we take this idea and first use it for images? And the answer is yes. If that wasn't true, I wouldn't be giving this talk. And so an example here is Pinterest. So here, Pinterest has this feature where you can select a part of an image, and it searches for similar images. You can imagine that this is super useful for fashion, or an example that a fellow worked on was to adopt cats. You don't really know maybe details about cats, but you just want to send a cat picture and be like, hey, I want a cat that looks just like this. And so these are the same. So you're trying to learn embeddings for images. And it turns out for images, it's super simple. You use what's called a pre-trained network. So here this is VGG16, a very popular network. And at the end here, it just predicts, so those classification networks just predict like, hey, this is a car, this is a cat, or this is a door. If you take the layer right before, it's actually learned these very useful embeddings sort of by itself, which is super cool. So you can just use these as embeddings and then find similar embeddings to an image to make it work. So this is a very high level, and let's just dive into some code to sort of see how you could combine both. So I think I have one more slide here. Yeah. So the approach I'm going to use is very loosely adapted from a paper called Devise, a deep visual semantic embedding model. And I'll go more in depth into like exactly what we're doing. But the idea is, how Google embedded the emails that you would get and the responses that you could send in the same space? Well, the idea is like, okay, well, can we do the same? Can we embed, these images that we have and text in the same space And then if we do that, then we'd be able to use this model to just generate a bunch of tags for any image, or search through our images by just inputting text. Cool. All right, so let's dive into a demo. Maybe this will work a little better than the PowerPoint. There we go. Beautiful. Okay, cool. So here, I'm going to show you how to do this. So this is actually pretty easy, and this paper is honestly one of my favorite papers on the topic, because compared to all the complex models that I showed you, you're going to see that this is actually quite simple and strikingly effective. So again, feel free to ask me questions. This will, go more into the nitty-gritty of the code. So yeah, Sven, feel free to interrupt me if anything pops up. Cool. Awesome. All right, so let's start with loading the data. So the data set I took is a data set of 1,000 images divided in 20 classes, 50 images for each class. It's a pretty simple data set, and I just wanted to use it to test things out. To be clear, for most of this tutorial, we won't be actually training anything on the data set. We're just using it to see how our models do. Then I load glove vectors, which are sort of these word vectors we talked about. They've been pre-trained on Wikipedia, and so they already sort of encompass the meaning of words very well, and you can just download those online freely. We're then going to just basically load those images and load the word vectors corresponding to our 20 classes. So our 20 classes are, pretty standard. They're like TV, monitor, boat, bus, dog, person, chair, bird, etc. You can see them here. So, pretty standard stuff. We load them. We have, 1,000 images and 1,000 word vectors that are sort of repeated. They're just like, you have 50 of the word vector boat because there's 50 images. And just so you have an idea what it looks like, this is sort of like what the classes are. So here's a photo for airplane, here's a photo for bicycle, bird, etc. So they're pretty reasonable. I'll show you later, the labels are kind of crazy. So here's this cat. The cat's pretty small in the image. This one's chair, right? Which maybe that could be person, right? The chair's here, and there's 3 people right there. And so what's interesting about this problem is that in many data sets that you'll face in the real world, labels are always noisy. It's very hard to label something as one thing. There's usually multiple things in the image. And so that leads to a lot of problems with the usual way to do things. Cool. So now we're going to use, we're going to do just what we did, what we showed to get the image embeddings. We're going to use a model that was pre-trained on a large data set. So again, you can just download this. These models are freely available, and use it to generate features of our images. So, you can use the model to predict what's an image. Is it a cat? Is it a dog? And use the layer just before to sort of get these image embeddings. And so here we generate these features. Because this takes a little bit of time, we have to run our model over all the images. I've saved them to disk so that it's fast. So here you can cache it. Our model, again, is VG16 without the last layer. This is the model description. This is sort of very verbose. But basically the idea is the model that we talked about without this part here, right? We just remove this. And so we have this 4096 layer at the end. So to give you some context, here are the first 20 images. Each row is an image, and then they each have sort of this thing of length 4096. That's just this embedding vector. And so let's see if this embedding vector works well to do image search. So we can take an image, get its embedding, and then just look in our fast index to find similar images. If our embeddings work as well as we had hoped to, that means that if we could take a photo of a cat, we'll be able to find other photos of cats. And to make this a little more challenging, I've used the fact that we have noisy labels. So here, as I said, the labels are often noisy, and so there's more to an image than its label. And so in our data set, we have a class that's cat. We have a class that's bottle. So which class do you think this image is labeled as here? Is this a cat or is it a bottle? I think most of you, would probably guess that the label of this image should be cat. The cat is like front and center. There's maybe a bottle in the dark corner in the background here. But of course, the right answer is bottle. So the real label of this as well. So if we were to just do the naive thing of say like, oh, well, okay, this is an image of a bottle. We've trained our model. It's a bottle. Let's find similar images. We're just going to find similar bottles. But if I tell you like, hey, Sven, could you find similar images to this? And you're a human, you're not going to find like other shampoo bottles or other soap bottles. You're going to find other cats. And so let's see how our image search does. So we use our index of these vectors above here and search through them. And here we can see that, oh, this is great. This has found other cats. This works super nicely. And all that we've done is just look for, so we take the cat image here, we take like one line, right? And we just find vectors that are close. So we just do like distance between those two vectors. And it's like, oh, we have a bunch of cats. You'll notice, interestingly, that here we have an image with bottles. So it has picked up on some of these bottles. And this is okay, but do you think we can fix it? there's actually a little trick that you can use, and I haven't seen this published anywhere. And this Dewan, a fellow in the data science program, actually came up with this idea, which I think is brilliant. Which is like, well, what if I know that I want cats? I don't, here I give you an image, I say find similar images, but what if I say like find similar images of cats? Well, we have a classifier that we use this with, and this classifier has the class cat. So what we can do is reweigh that last layer, those embeddings that we have, by the weights of our target class. This is definitely a more like low level, kind of maybe harder to explain approach, but basically you just multiply it by a bunch of weights that are, again, in our pre-trained model. And then you try to just do the same sort of comparison with these. And we see that, oh, we still get cats. Oops. But the bottle's gone. That's interesting. What's funny to me as well is at the bottom left, I don't know if these are cats. These might be sheep, but you can see how the model can be confused because they look similar. It's like a very small thing. Awesome. So this works very well for images. What about words? Could we use a similar approach for words? The answer is yes. So we took these pre-trained vectors, and you can see what they look like. So here, this is the word vector for word. These are length 300, and so they're sort of the same, just a list of 300 numbers. This is for the word vector. And then we can just use our index and say like, okay, I give you a word. Can you find similar word? And so you can see that, R, for example, let's find similar words to the word R. And what's the one here? Oh, were, okay. Or these and those and all. And you can see that these are all sort of words that sort of happen within the same context. So we can see that, okay, this word search is pretty useful. Now, we get image search, we got word search, but the whole goal was to combine both. And so here, this is the only part where we're actually going to train a model, but it's a very, very simple one. And basically, the idea is, so here we have the same model as before, but we're going to add 2 layers. And so this is definitely going to get a little more technical here, but basically this was the end. This was our last model. It stopped here. Here we're adding 2 layers. So dense layer, then some activations and another dense layer to get to an output of size 300. Why is that? That's because our word vectors are size 300. And so basically what we're trying to do here is we try to predict the word vector associated with the label. So to go back up here, we take all of our images, and then we take our model. We keep the weights that we had so that we don't have to train it from scratch. And on top of it, we learn like a simple model that's going to say like, okay, I take those image features that are really informative, and I'm going to learn to predict. So for this one, the word vector associated with bicycle, and then the word vector associated with bottle. And then the hope is that in a traditional classifier, you predict a class, but the class doesn't really have a meaning. Like it's just a category. The way that you say whether it's a cat or whether it's a bottle is that it's index 4 or index 6, but there's no semantic meaning. But if you try to predict word vectors, then you can imagine that your classifier is going to sort of learn the semantic meaning of word vectors. It's going to be like, oh, well, when I predict bicycle, like, the first 20 dimensions of the word vector tend to be high. And that's the same for bus because it also has wheels, and car because it also has wheels, but it's totally different for people because they look very different. And so you can imagine that the goal is that this will allow our model to very simply generalize. So to give you context here, we do this and we train it on 1,000 images. So 1,000 images is nothing. ImageNet, which is sort of what these models are based on, is 1,000,000 images. So expecting to get anything of quality that generalized for 1,000 images is insanity. And yet with this model, you can actually get there. So here we add our 2 dense layers, as I said, and basically we train it. So I haven't even trained it for that long. And to be very honest with you, I trained it overnight. And when I stopped it because I just sort of ran out of time, but it was still converging. So it was still getting better. So this is even the best version of it. But basically we train it, and then we, I save the model, so I'm loading the checkpoints. And so we build an index of the word vectors and of the images, just like we did before. And then we can see that the embeddings of the images, so before they were size 4,000, now they're size 300. Okay, so now we can do something simple. It's, okay, for each image, I use my models to predict this word vector, and then I find similar words. So here's an image of a cat or bottle. What are similar words? Okay, cat, litter, raccoon, monkey, leopard, puppy. Okay, that's reasonable. What's really interesting here is that if you use a normal deep learning model, the ways that it will be wrong, if it doesn't predict cat, it'll predict things that are semantically completely different. Again, like car, street, tree, that kind of stuff. But here it's understood like, okay, maybe it doesn't get that it's a cat, but it definitely gets that it's an animal. It's understood these features. What's even more impressive, and I think really cool in terms of combining these representations, is that you can now use it to search with any word. So here, one of our classes is dog, so we can just search for dogs in our data set. Oh, this gets us. So here's all of the images that are closest to the word dogs. Again, we've both put them in the same space. And so to do this, this is instant. You've saved all these features to disk. It's just like a lookup in a database. You don't need to run any machine learning once you've done it once. And so, oh, you find all dogs. This is relatively easy because we have the class dog. What you can do, you can use classes that aren't in our data set. So in our data set, there's no class for ocean. The closest thing is boat. So if you just look for like, oh, I want images of the ocean. Huh. All of a sudden you can find all images of the ocean. That's pretty nifty. We never train on the ocean. And yet our model very quickly figures out that, oh, well, if there's images of boats and boat is similar to ocean and you're looking for ocean, then I guess those images would be a good result. And this was done without any sort of need for feature engineering. We just basically found an intelligent way to embed them in the same space. But you're going to tell me, okay, well, boat and ocean, they're still pretty close. So let's try to push our model a little bit. And then we're going to go for very hard things. And I want you to remember that these results are with a model that was trained for like 5 hours on an extremely small data set. So here we have tree. Tree is completely different from anything that we have in our data set. So obviously our results are a little more noisy, but you can see like, oh, a plant. Oh, this tree in the backyard. There's no tree class, by the way. I think that, well, I guess these are potted plants. So it learns that this is what trees are because it relates it to potted plants. So even harder, because this is still pretty close. Let's do street. So there's nothing close to street here, but yet our model just learns to pick up on all. Here's a street in the background. Here we're in front of the street. Here's a street here. Here's a street here. Here's a street there. You could just search for any word in the English language and find images that map to it. And all you had to do is just change your image model to output word vectors that you had trained previously. This is an extremely simple process. It took me, as I said, 5 hours to train it. You could use it in a very general way. You could train it longer. You could train it on more data. The whole code is right here. It is actually very short. If you look at it, it's a couple hundred lines. I'll make it available shortly after this talk, and I'll send you an email about it. But yeah, this is basically the idea of how you can sort of short circuit a lot of these things to build a model that's both simple, but also think about how scalable this is compared to what we've seen before. You can just, if you have a huge image database, you can just overnight run your model and then just get these vectors of size 300 for every image. And then you just have Google search. You just need to search through these vectors. And searching through vectors is infinitely fast compared to doing any sort of machine learning. So yeah, that's about it. That's most of sort of what I wanted to talk about. If you have any questions, I've put my sort of contact info here. And so feel free to reach out if you're interested in these projects. We do a lot of those at Insight. So feel free to reach out if you want to become a fellow, or if you think that these are really cool projects and the people that are able to make them should definitely work at your company. We also partner with a bunch of companies to introduce them with our awesome fellows. So I mean, I hope you enjoyed it. Again, feel free to reach out to me or to Insight, and yeah, I'm happy to take questions.
All right. Thank you, Emmanuel. It's been a really cool talk, especially the vectoring, like a combination of NLP and like the image search. That's pretty awesome. I have a question. Well, is that just a research model right now, or do you apply that anywhere, or do you plan to apply that?
The device model?
Yes. Well, the demo you showed.
Oh yeah. So that's interesting actually. So yes and no. So to be clear, the idea came from this research paper. That was really cool. I very lazily implemented it by just seeing how many things I could not re-implement. So I just basically only took the idea of just predict word vectors from images. They did a bunch of other stuff to make it better, but I found that worked well enough. And the reason I sort of built it, and I'm trying to build it as sort of this general purpose thing, is that this is something that if you do applications, ends up being a building piece of many other applications, right? Like you want to just use it as a data augmentation step to find similar images, or you want to use it as sort of a post-processing step to just check that your results are good, or you want to use it as part of a pipeline. And Insight Fellows use similar things all the time. And so the idea is that I think other people in the industry do as well. And so that's why we're sort of building this, open sourcing it so that people can just use it. And people that have tons of compute can also retrain it on more complex data sets, and it'll only get better.
Cool. Yeah, we had one follow-up question to the first question we had about CNNs and GRUs. If you know or can provide like any link or GitHub repository where there's an example of how that works.
Yeah. So if you go, so here's a link to our blog. So okay, well, my PowerPoint. Okay, anyways, so there is a link to our blog, which I can just type here, blog.insightdatascience.com. And in our blog, that post, so if you go to AI here, there's a post on that, and there's the full code is available to this guy here. Automated front-end development, so it's done by Ashwin, who's a fellow in our previous session, and he has, I think, just look for GitHub. Yeah, he has a whole GitHub here. It was a pretty popular repository, got a bunch of stars, etc. So here, this is a training script for like a GRU and a CNN, so you can just sort of look through that.
Sweet. Yeah. I think we'll send follow-up emails anyway, and we'll provide all these links. Yeah, and as you said, the code.
Yeah.
Perfect. Yeah. We don't have any other questions right now, I think. So yeah, all that's really left for me. Oh, well, there's something coming in right now. Of course, when I say there's nothing else, then people. Hey, somebody's asking. Let me just read this real quick. Oh, it's about generating images instead of recognizing them with the example you gave. The example is if you have an image of a red bird where the word associated with the image is red bird, and you want to use that to generate a similar image, but with a blue bird, for example. The question is if this concept could form a first step towards that, or how that could be.
Yeah, that's a super interesting question. So I think to look back on here, where's this? I have this network graph here. Okay, so it would be hard, basically, is my short answer, because the idea here is that once you take your image and you boil it down to this vector, you've lost a lot of information, right? So this was 200 by 200 pixels, and at the end you only have 4,000. So you have very little information. So recreating an image only from that is hard, and it's definitely doable, but it's hard with this simple method of like putting the vectors in the same space. The ways that people traditionally do this are with GANs, or with conditional GANs, or with autoencoders, which sort of explicitly try to model. So if you have an autoencoder and you have a bunch of images of red birds and green birds and yellow birds, and you want a blue bird, you can just sort of put them through your autoencoder, and then in the autoencoder you can sort of change the latent space, or if you use a GAN, you can sort of condition it. There's conditional GANs so that it can generate blue birds. But the short version of the answer is you need models. For now, at least, I haven't found any simple models to do that. You need models that are a little bit more elaborate, a little closer to sort of the ones that we talked about at the start of the talk.
Cool. Yeah, well, all right. One more question coming up from the person who just asked this question.
Sure.
I think we'll need to allow some time to type it up.
Oh, you can see it here. All right. Cool. Maybe I'll do this as well. Oh, there we go. Yeah, take your time. And if there's anything that was unclear, also let me know.
Here we go. Yeah, how much of this work is limited because of compute power? This person wants to know. It mentions the recent open AI research used dozens of GPUs, but yeah, I guess you didn't do that because you trained it on a very limited set. So how's that limited?
Yeah, no. So this is sort of the idea is that for a lot of projects at Insight, we have GPUs that we just use for them. I'd say that there's sort of three tiers of projects. And one is the sort of OpenAI, DeepMind, mind-boggling scale. So these are things that are available to very few people, where they use, hundreds and hundreds of GPUs to do sort of research on things that are completely unexplored. For most computer vision and NLP applications, even if you wanted to build this classifier that we used at the start, so we used a pre-trained one. If you wanted to build it from scratch, you just need one GPU in a couple of days, and you'd be fine. In fact, you can train these models on AWS or Google Cloud for like $20. So it's not nothing, but it's definitely doable. For this particular example that I showed you, you need even less than that. I didn't even use a GPU, and that was sort of the point. That was a challenge I set for myself, which is, well, could we get good image search working with no compute at all? And so I took a pre-trained image model, pre-trained word vectors, and then the last part where I just learned this sort of mapping. As I said, I ran it on my laptop for 5 hours. And so, I had my laptop plugged into the computer, caught up in the last season of Westworld and just had it in the background. And didn't need any special compute, and I don't have a particularly powerful laptop.
Cool. Yeah, that sounds promising. Sweet. All right. I think our time is also pretty much up. What is left for me to say is thank you so much, Emmanuel. This was a really, really amazing talk. For everybody else, we'll make the slides, the video of the session, and resources and links. And I think there's a blog post that's coming up, Emmanuel.
Mm-hmm. Yep.
We'll make all that available, and we'll send a follow-up link. A follow-up email with links to you, and then you can check all that out.
Awesome.
All right, sweet. Well, thanks again, Emmanuel, and everybody else. Thank you for joining. We'll hope to see you next time. We're going to have exciting webinars coming up soon. Again, we'll send out emails about that. So keep in touch.
Cool. Thank you.